So 53A is similar to number 43, except now we're dealing with an acid. Letter A isn't too bad. We're looking at adding a strong base to our weak acid and wondering how much do we have to add in order for the pH to be equal to the pKa. Well, that's a very special point. That's halfway to the equivalence point. Okay, well, the equivalence point is where the moles of strong base equal the moles of weak acid. So if we're halfway to the equivalence point, we have this many moles of weak acid. How do I know that? Because we've got 1 liter of it at 2 molar. So if I got 2 moles of my weak acid, then I'm going to need half as many moles of my strong base. So the first one's not so bad. B gets to be a little bit trickier. So we know that the pH is equal to the pKa plus the log of the conjugate base over the acid. Our pH in this problem, we want it to be 4. The pKa is the negative log of the Ka, which is 1.8 times 10 to the negative 5th. And I looked up that. So the pKa is 4.74. So I plug in my numbers. And end up with the ratio of 0.181 So for every one of these, for every 1 mole of weak acid, I'm going to need 0.18 moles of the weak base. Okay, so we make the weak base by adding the strong base, because just like in problem number 1, those two things are going to react. So the sodium hydroxide reacts with my weak acid and it produces my weak base. Now, sodium's attached to it. Well, it's not really attached to it because it's a salt. So beforehand, I don't know how many moles of this I'm supposed to add. I know I've got 2 moles of this, no moles of this. Afterwards, all my base will have reacted. I will have lost some moles of that, and I'll have gained some moles of that. Okay? So the ratio of my conjugate base to my weak acid, the ratio that I'm looking for is 0.181 to 1. Okay? That's the ratio I'm looking for. So then I just have to do a little bit of algebra. And 307 moles of base. Okay, and then we just do the same thing for letter C.